Without EVs, our planet is going to boil. Everything about EVs is a scam. EVs are way more efficient than traditional vehicles. EVs don't have any range. We have to end oil. So who was right? And why am I even talking about this? First, I guess I need to tell you who I am. My name is David Jazowitz, or Jazz, to the people who know me. My background is in mechanical engineering, and I have been involved in electric vehicles in various ways for decades. Starting in high school, I attempted to build an electric vehicle from a donated forklift and some parts that I could scrap together. This seemed like a good idea after years of racing radio-controlled cars, but I might have been a little overly ambitious with my $25 budget. Looking back, I had a bit more motivation than direction. In college, I took a little more research-oriented approach. After some time with the Purdue Solar Racing team, I completed a research paper on the state of electric vehicles in the late 1990s. After graduating with a degree in mechanical engineering technology, I worked in the automotive industry, including some time at General Motors in the electric powertrain division. This here is my favorite souvenir from my time there. This was a cover for an Allison drive system that was used on the electric buses. It's a bit bigger than your average EV inverter system. I worked on several projects there. They were all post EV1, but they were well before the explosion of mass market electric vehicles. After that, I did some work on Discovery Channel, converting gas cars to electric, and more recently, I did a personal EV project. I'm not here to tell you the greatest trends about everything EV, or tell you that everything about EV is somehow bad. I want to look at where we're at, how we got here, and what we can expect for the future. I could easily spend hours going through the details on technology, science, and the politics around electric vehicles. So I've had to really work to whittle down the scope of this video to keep it interesting and useful. I look forward to engaging in the conversations that will result, and I want to discuss them in future videos. Given the broad overview, there will be a lot of points of conflict as we get into the nuances. I encourage the debate, so let the fireworks fly. Let's start off at the beginning of EVs. The first electric vehicles started to hit the market around 1870, and by 1900, 20% of cars on the market were electric. Because of these high early percentages, many people think there was a grand conspiracy that ended electric vehicles. However, the main driving factor that caused electric vehicles to fall out of favor was the same problem that electric vehicles have always had. After 1900, technology for internal combustion engines continued to improve at a rapid rate. However, electric vehicles were limited by their batteries. Back in the early part of the 20th century, the only option we had for battery storage was low-tech lead-acid cells. Also, the electrical infrastructure to charge these batteries was a small fraction of what it is today. Gasoline was easy to transport to rural areas, allowing for internal combustion engines to be more appealing for long trips, and it served a wider customer base. As the popularity of internal combustion engines increased, this led to a lot of pollution in urban areas. However, the infrastructure and battery storage issues with EVs continued to keep them from being a viable solution to the problem. Fast forward almost 100 years, and we saw the first renewed attempt at a real electric vehicle program when General Motors released the EV1 in 1996. The first prototype of this car was announced in 1990 as the GM Impact, which I think their marketing division decided was probably not a good name for a car. In the time since the first electric vehicles were produced, a lot has changed in the automotive industry. To many, it looked like the electric vehicles were finally going to get the chance they deserved. While some small efforts were put forth in the 1970s during the gas shortage to create custom-built electric vehicles, this was the first time that a major manufacturer was looking to step into the game. It was not really a big surprise that General Motors was the company to take this on. GM dumped a lot of money into electronics technology in the 80s, which put them at the forefront of this type of research. Many of us remember the General Motors cars of the late 80s and early 90s that had a lot more electronics on them than their competitors. Many of these technologies turned out to be a nightmare with durability problems, and in many cases, it provided customers with features they didn't really even want. However, this allowed General Motors to gain a base in automotive electronics. When the EV1 came into the market, its performance was impressive, and it received a lot of attention for its innovation. It was the release of the EV1 prototype, the Impact, that really spiked my interest when I was in high school. Analysts predicted tens of thousands of these cars would be sold every year. However, The truth was that much of the technology and the problems associated had not really changed that much since 1900. The first run of EV1s were still using lead-acid batteries, not much different from the cars from 90 years prior. This is similar to what we still use as a starting battery for most of our internal combustion engines. The first EV1s used a fairly standard Delco lead-acid battery, and it was not until 2000 that they even switched over to a Panasonic advanced lead-acid battery that used glass mat technology. This is the same technology that's used in high-end modern ICE car batteries. So you can in some ways thank the EV1 if you're taking advantage of this technology today. However, even with the improved batteries, the car only had a 55 to 95 mile range. Towards the end of the EV1 program, a nickel metal hydride battery was offered, which increased the range to 75 to 130 miles. In the few times I brought one of these cars home from work, I have to say it was more of a novelty than a true fun driving experience. They overall drove well, but they were cramped because so much focus had been put into making the car an aerodynamic teardrop shape, and after packaging the batteries, there really wasn't a lot of space left for the passengers. However, they were fun to do some mild burnouts with. The EV1 was actually a bit of a sleeper by 90 standards with a 0 to 60 time of under 8 seconds. While battery technology had not improved much since the first electric vehicle offerings, there had been some advancements in motors and power electronics. The original electric vehicles used DC motors that were not much different from the motor that starts an internal combustion engine or that we still use today in many DIY EV conversions, forklifts, and golf carts. The EV1 used an AC motor for increased efficiency that was similar to the AC motors found in most industrial equipment. This motor was not functionally a huge deviation from the first motors that Nikola Tesla invented in the late 1800s. However, one big thing did need to change, and that was that the motor could not be plugged into an AC power grid, and it had to be lightweight. All batteries provide DC power, so an inverter was needed to convert this DC power into AC. Also, traditional induction motors are very heavy for their given horsepower. The EV1 motor produced 137 horsepower, but only weighed about as much as the traditional 10 horsepower industrial motor. The prototype motor and control system were designed by AC Propulsion in San Dimas, California. To make all this work, the motor and inverter had to be water cooled. This is very important to this day with electric vehicles. When I was at General Motors, I worked a lot with the dyno lab, and one day they forgot to turn on the cooling water before doing a test run on a motor, and the inverter pretty much smoked immediately. The EV1 was limited to 80 miles per hour, but the prototype Impact hit a speed record of 183.3 miles per hour in 1994 on a Texas track. I spoke with one of the engineers on the project, and he told me that he put a handwritten note on the dash not to exceed 180 miles per hour in first gear. Apparently the driver didn't listen. To my knowledge, it was essentially a stock vehicle but had the addition of a couple extra batteries to increase the voltage, and they put a tail cone on the back of the car to make it more of a completely aerodynamic teardrop shape. That was not too bad for 137-ish horsepower. I don't claim to be an expert on the EV1 because my time working there was in the Gen 3 and Gen 4 projects when the EV1 was Gen 1 and Gen 2. However, I was with the company during the time of the dismantling and crushing of the EV1. In my facility, the only disassembly we did was of the inverter modules. I was friends with the producer of the documentary Who Killed the Electric Car, and we had some pretty lively debates over General Motors' decision to end the program. From our conversation, he seemed to believe that it was a grand conspiracy from the oil corporations to kill the car. From my perspective, it was more of a business decision. The EV1 project cost General Motors about $1 billion from start to finish. They built a little over 1,000 cars, which comes out to almost $1 million all in for those EVs. General Motors only offered the EV1s for lease, and they were not available for purchase at all. If General Motors was to sell the cars outright, they would have been required to supply the parts for the car for 10 years by federal law. By this point, General Motors was making most of their money on SUVs, and the small electric car just did not really fit into their business model. We can debate if this was the right decision for GM, but that'll have to wait. I personally believe if GM wanted to, they could have continued this technology development and become the leader in EVs. It is open to speculation if that would have been the right decision, but I think it would have been a really hard sell to the stockholders. Regardless, it would have been almost impossible for those endeavors to have survived the 2009 Chapter 11 bankruptcy. After the EV1, General Motors diversified their research and looked into a lot of different technologies. Working there, it did feel a little ADD compared to Toyota's all-in focus on the Prius. However, I think GM knew they weren't ready for prime time and wanted to focus on development. That was when they made the electric bus drives that I mentioned before and some other hybrid technologies. I worked on a project referred to as a light hybrid. One of these was a belt-driven alternator starter that ran off 48 volts. The idea was that this could be used to shut off an engine and roll forward at a few miles per hour at traffic jams and stoplights. The engineers I worked with felt that this was a very worthwhile program because the system was relatively inexpensive compared to other hybrids and could be used on the biggest offenders of fuel efficiency. If you could save a few miles per gallon on a large SUV, the fuel savings would be greater than making an already efficient small gasoline car all electric. However, saying we improved the gas mileage on a Chevy Suburban by 4 miles per gallon does not have the same wow factor as saying a Toyota Prius gets 57 miles per gallon. A version of the belt-driven alternator starter system did make it into production, and the electric horsepower boost significantly improved gas mileage for in-town driving by reducing the need for gear shifting. I've not stayed up with this technology since working on the prototype, so speak up if you have some thoughts. I know I might have been a little drawn out up to this point, but I wanted to cover what I personally had experience working on. So let's skip forward to the current day. Attempting to not go down every rabbit hole, let's focus on what has really changed since the EV1. While there's been improvements in motors and inverters, the most impactful improvement has been in battery chemistry. Nickel metal hydride batteries were an improvement over the lead acid batteries in early electric vehicles. However, the technology had a lot of problems, including reduced capacity from memory effect, heat dissipation problems, and a high self-discharge rate. This was at best a stopgap until lithium ion and lithium iron phosphate batteries became readily available. Lithium technology quickly led to a revolution of portable electronics and cordless power tools. This technology naturally found its way into electric vehicles. However, this is where the comparison ends. While portable electronics may have a battery that weighs anywhere from a few ounces to a few pounds, an electric car may require a battery that weighs well over 1,000 pounds. This might be okay in limited run applications where supply chains can handle the raw materials. However, the requirement to provide the resources necessary to transition a large part or the entire vehicle supply chain to electric is completely unrealistic. In an attempt to be more realistic, if you've enjoyed the journey so far, I would appreciate it if you liked and subscribed, because I want to continue this conversation in the future, and I can't do it without your input. Otherwise, I'll just start blabbing on about why you shouldn't lick a flux capacitor or something. Most of the current electric car agenda focuses on the positive environmental aspects of the technology. The quoted statistics assume that vehicles will be charged by renewable energy, such as wind or solar. Current statistics from the U.S. Energy Information Administration claim that 21% of electricity generated in the United States is from renewable resources. However, these numbers are extremely skewed. In the best case scenario, these statistics do not cover the energy that goes into creating the technology or the fuel that's required to maintain it. Almost all the energy from these tasks come from fossil fuels, and there does not appear to be any changes coming in the near future. Another problem with green technologies is related to end of life. Energy generation projects are typically calculated and compared to each other, assuming a 30-year life. This can make renewables such as wind and solar appear overly optimistic, as they may only have a 20-year lifespan, yet are compared on equal footing to a traditional coal or natural gas-fired plant, which may last for 50 years. Also, there's a major financial factor involved. Installing wind or solar projects can require about 80% upfront to complete the project, with an additional 20% for maintenance over the project's life. However, with traditional power plants, the upfront cost is more around 20%, with an additional 80% being spread across the life of the project for maintenance and fuel. The large upfront cost has been managed over the last 20 years as baby boomers have been investing for retirement. This was a huge boost for projects that otherwise would have gone unfunded. However, they're going into mass retirement, and they're being replaced by a smaller Gen X population. Retirees pull investment money out of the system to live on instead of putting it in. In this environment, large-scale projects with huge upfront costs will not be as economically feasible. The problem does not end there. To transition to green technology, whether we're talking about electric vehicles or the renewable resources to charge them, materials are just not available. What we think of as Green energy requires much more exotic materials and more energy-intense processes to manufacture them. If we were to do a full green transition to eliminate fossil fuels, we would need a massive increase in the current mining operations. We would need exponentially more cobalt, lithium, nickel, graphite, and copper, just to name a few. By most estimates, we would need over 100 years worth of mining at the current rate to do the full transition. Keep in mind that most mining equipment runs off diesel, and the processing plants are very heavily powered by fossil fuels. I don't care how badly you want this to happen or how much legislation we push to force the direction of the industry. You can't legislate resources into existence on that scale or force new technology innovation to happen. On top of that, mining is one of the most environmentally destructive activities humans can do. Ironically, the people demanding the green transition are the same people blocking the mining required to make it happen. Even if you ignore most of this data and just want to look at how electric vehicle operation is more carbon friendly, if that's your narrative, it can easily take up to 10 years for an EV to break even on the carbon output compared to gasoline vehicles once you factor in the carbon that goes into manufacturing these cars. Another often overlooked factor is the recycling of electric vehicles and other green technologies. The most energy intensive part of making electric vehicles is the lithium batteries. They are also the least recycled aspect of the entire car. It is less expensive to mine new raw materials than it is to recycle old batteries. Current numbers estimate that only about 5% of lithium batteries are recycled. Compare this to 99% for lead acid batteries. This would make lead acid batteries an ideal solution if they weren't so damn heavy. Speaking of heavy batteries, make sure you stick around till the end where I'll share my personal EV, and it's probably not what you think. Looking back at the early 1900s, it came down to battery issues. When I wrote my report in the late 90s on the state of electric vehicles, it came down to battery issues. If we look at today's electric vehicles, it's still about battery issues. We have new technology in solid-state batteries coming, which looks to improve the life expectancy and capacity of lithium battery. However, we still have the recycling program. Until we can come up with a way to reliably and cost-effectively recycle lithium or another cost-effective recyclable battery chemistry, we don't have a solution. We hear concerns about running out of oil, but what about depleting all the vital minerals that we use to create electric cars, because they get disposed in landfills? Until we can come up with a cost-effective way to recycle batteries, EVs just aren't an ideal solution. Another aspect that is not talked enough about is battery life. I've seen reports of newer vehicles being scrapped because of battery failures. There's also a lot of data showing that battery packs will last a long time. Regardless, they do have an end of life. For someone who purchases a vehicle and uses it within its capacity on a daily basis, this may not be an issue. However, I think it's important to look at how the finite life of a battery affects downstream users. There are a lot of people who have older vehicles that they use for minimal travel and can't afford a new vehicle. I, for example, have a 1-ton Chevy diesel truck that's over 20 years old. I do not use this truck often. However, when I need to move a heavy load or I need to pull a heavy trailer, I do need it. A vehicle like this might be worth $10,000, and it will probably still be in reasonable shape in another 20 years. However, if this was an electric vehicle, we can reasonably assume that by now, the battery would no longer be usable. Most likely, a battery in a vehicle this large would be somewhere between $20,000 and $30,000. As soon as a part in a vehicle is more expensive than the vehicle's total value, it's worthless and it gets scrapped. There's an entire demographic of people who rely on the secondhand market for their transportation needs. If low-cost internal combustion vehicles are no longer available, a huge percentage of the population will become underserved. Given these challenges, where is the glimmer of light for electric vehicles? First, I cannot really endorse most applications that have a suitable traditional internal combustion engine substitute until they get the battery recycling issue solved. Let's assume battery recycling becomes affordable and we see lithium recycling on par with the recycling of lead acid batteries. This would be a game changer for many applications, but not all. Much of the EV market exists only because of government mandates and incentives. If we want to see the real potential of any technology, we must look at where it's being successfully used in an unsubsidized environment. One place electric propulsion has existed for a long time purely because it works is in forklifts. The reason it works so well is because the vehicles do not need to move at high speeds, and they do a lot of stop and go travel. Plus, weight is not an issue. We can compare this to city driving. Electric vehicles excel in stop and go environments in ways that gasoline and diesel vehicles just can't compete with. The ability to not use any significant power while stopped and boosting the battery pack through regenerative braking are two of the key strengths. First, let's look at why EVs don't do well outside of an urban area. Vehicles that travel at high speed use a large percentage of their energy to overcome wind resistance. This quickly eats into the limited energy reserve capacity in the battery. If we compare a high capacity Tesla battery to a gallon of gasoline, gasoline has an energy capacity about 45 times of what the Tesla lithium ion battery pack has per pound. If we are generous and say the Tesla is 3 times as efficient as an internal combustion engine, we must still have a battery that weighs 15 times the weight of the equivalent amount of gasoline. This is why a gasoline vehicle may need 100 pounds of liquid fuel, while electric cars may need a battery that's well over 1,000 pounds. Not only is this battery heavy, but it takes up a lot of room in the vehicle. If we want to increase the vehicle capacity, our only option is to add more batteries, which in turn makes it heavier and less efficient. The place where electric vehicles can gain back some ground is in city driving. We should want to see EVs use where their strength is and not try to compete on their weaknesses. The ideal EV application may not be in replacing your personal gasoline vehicle. There are cases for EVs that only need a 100-mile range. Fundamentally, electric vehicles can be very reliable if we do not try to cram in a bunch of unnecessary technology in them. They do not need as much maintenance, and outside the battery packs can be made at a reasonable price. I think the best use would be for vehicle share programs inside a city. There are a lot of people who would like to have a car available to them in a congested area, and they don't want to have to worry about maintaining or finding a place to park it. If we were to treat electric vehicles more like a self-service taxi that could drive where you need it and then you can leave it for the next person, it would eliminate a huge expense for the user, reduce traffic, and solve parking issues. An electric vehicle with a 100-mile range could drive around town for hours without any problem. Because these vehicles could be used by multiple people, it could drastically reduce the number of cars on the road. This is by no means an in-all solution to replace internal combustion engines. I see this technology realistically replacing about 10% of the vehicles on the market. Given that these vehicles could be shared, that might eliminate another 10%. However, this is a right-sized solution to a right-sized problem. These vehicles will be used most in polluted areas where they can be the most beneficial. This is not ideal for suburb commuters, but it would be ideal for people living in the city or those who need a vehicle during the day while they're in the city. This could be a way to supplement the public transportation system. As the United States is not known for having an extensive rail or bus system, there could be an opportunity for EVs to round this out. If we can have some better thought out public transportation, combined with the new work from home culture, this could further reduce the need for another 10 to 20% of the cars on the road. In my opinion, trying to add larger and larger batteries to EVs to make them compete with traditional vehicles is a misallocation of resources. Right-purposed cars could use 1/3 the battery, allowing 3 times the electric cars to be made with the current battery production. Also, we have surplus energy capacity at night using our current power grid, so we might as well use it to charge cars. I do think EVs are a valuable area of technology and needs to be continually researched, and I hope one day battery technology will catch up with our needs. As I mentioned earlier, I would like to tell you about my personal EV ownership. So yes, I do own an EV. A while back, I purchased 40 acres of off-grid property and I needed a way to get electricity to it. I could have used a gasoline vehicle and drag around a gasoline generator, but that would have been a huge waste. Oftentimes, I'd be working on a project and I just needed to run a few power tools intermittently. This is a perfect situation for battery storage. I picked up a utility truck at an auction, and instead of using it primarily to transport things, I used it to transport my power. I put together another video of how I set up the battery system and covered the top of the vehicle with solar panels. I can use it to drag my tool trailer around the property, and it brings its own 110 and 220 volt power with it. With the solar panels on top, I don't need to worry about charging it, which is perfect because my nearest power line is 10 miles away.